All right. What we're going to do in this special mini lecture, so to speak, is to clear up some common points of confusion, unnecessary confusion, while increasing our depth of understanding of the Boltzmann equation, entropy, and maybe a little bit about our universe. Okay, so that's just a zinger at the end, but it is kind of interesting. So what have we done so far? We considered n hard spheres that are basically in space, and they undergo perfectly elastic collisions among them. Okay, so we defined the 6 n-dimensional phase space. So we have n hard spheres of diameter sigma, and they're elastically colliding. And then we define this 6 n-dimensional phase space basically corresponding to the centers of each of those n hard spheres, and centers have 3 dimensions each, so that's 3 n dimensions. And then that is the velocity space, right? So we have 3n dimensional space that contains R1, R2, R3, up to Rn, which are basically centers of each of those spheres. And of course, this phase space has holes in it because spheres cannot penetrate each other, right? So at best, the distance between R1 and R2 is greater than or equal to sigma. Okay, so it is a large phase space with holes in it. And then we have the 3n dimensional velocity space up to Vn, right? So this does not have any holes in it, right? Taken together, we call it Dn. And then we defined a probability density Pn over this 6n dimensional phase space, V1 to all the way up to Vn, right? Just for completeness, let's say Rn, Vn. So this is the joint probability density over that 6n dimensional phase space. And this basically satisfies, it's very easy to show, we did this already, dpn by dt plus summation I equal to 1 to n vi dot d by dri pn equal to 0. Okay, so this is the Liouville PDE, not to be confused with the Liouville PDE in our operator setting, although there is, there is certainly some level of connection. But this is the Liouville PDE, and this is supplemented by some initial conditions for Pn and boundary conditions, right? Those boundary conditions live at the boundaries of, the so-called holes, okay? So like I said, if you consider the phase space corresponding to R1, for instance, right? So this would be sigma, and this would be all of the phase space around R1 in physical space. And then there's also the velocity space. So at the collision boundaries, right, this region here, we will have specular reflections, basically probably in equal to probability out, and then we have specular reflections. Okay, so that's the boundary conditions corresponding to Liouville PDE. Then what we did is we defined the one particle marginal F1 of R1, V1, which is basically you're going to be integrating your Pn d over all of those other variables, dr2, dv2, and all the way to drn, dvn. Okay, so this is the one particle marginal. And similarly, you have the two particle marginal, F2, R1, V1, R2, V2. And again, this is, again, you're integrating Pn over everything beginning with R3, okay, R3, V3, all the way to Rn, dVn, okay? And then we made the molecular chaos assumption, which was required to close the Boltzmann equation. And I'm not going to write down the details, but you know that basically you have F2 of R1, V1, R2, V2. Okay, so this does not leave the equations, right? So you can start with the Liouville PDE, and then you can keep doing all of your reductions using the techniques that we showed earlier. But what we will see is F2, even if you write an equation for F1, it will not be closed, right? You'll have F2 hanging out in the equation. So we introduced what is called the molecular chaos assumption, which again roughly translates to something like this. Again, please take a closer look at the notes. R1 plus sigma n. Okay, so I just want to write this. Well, okay, let me write it more clearly. Okay, so that there is no confusion, right? If you look at the first BBGKY equation, right, it'll have F2, it'll have this term in it. It'll have F2 of R1, V1, comma, R1 plus sigma n. And the reason why this appears is this term is a boundary term, comma V2, comma T, right? So this term is in the BBGKY equation, right? So we need to eliminate it. So the molecular chaos assumption is basically two particular assumptions. One is that all collisions are binary, and the second is this one. Let me write it, R1, V1, comma T, F1 of R1 plus sigma n, comma V1, comma T. Okay, so this is the molecular chaos assumption. Sorry, this is V2. Okay. And effectively what you're saying is just before two particles collide, they are uncorrelated with each other. Okay, so just before collision. Uncorrelated. Obviously, just after the collision, it is going to be correlated. So along with this, again, we assumed binary collision. Right? At any given time, a particular particle is only colliding with one other particle. And then we had the Boltzmann grad limit. Which effectively is a low density limit where it says your n times sigma squared is far less than 1, where n is the number density. Okay, so you can also write it in terms of the capital N. And basically, you're basically saying the number of particle times the cross-sectional area of the particles is basically constant, okay? So if you do that, we basically get the Boltzmann equation. And I want to write this out because write this out in its entirety, because there is some insight to be gained. V1 dot grad R1 F1 equal to the collision term, which goes as sigma squared V2 minus V1, right? This is always the differential velocity. And in fact, let's write this more carefully. Let's write this as V2 minus V1 dot N, and the magnitude of that. Then you have F1 of R1 comma V1 prime comma T times F1 of R1 V2 prime comma T, right? The prime is before and after collision. Before collision, you have V1 and V2. After collision, you have V1 prime and V2 prime minus F1 of R1 comma V1 comma T F1 of R1 comma V2 comma T, and then you integrate over the sphere, right? So this is the inner integral is an integral over the sphere. Let's call it the contact sphere. And the outer integral is over all of velocity space. Okay, that's in R3. So we have dV2. Okay, so this is the Boltzmann equation. And this is what we derived. Now, you can show that there is something called the H theorem, which shows, first let's define H. H can be defined in this form, minus integral F1 log F1, okay? And let's do this over, I'm just going to call it dV, and this dV is basically it's a 6n dimensional space, right? Because that is the space over which F1 is defined, right? So here we had dn sigma, whereas this would be, let's call it d1 sigma. Okay, so this is the entropy of the one particle marginal, and the H theorem shows that dH by dt is always greater than or equal to 0. Okay, the solution of the Boltzmann equation, let's call it equation 1, gives you F1, and the entropy of F1 always increases or stays constant. Okay, so this is the H theorem, and there is a lot of confusion around this because first of all, people say, oh, we started with perfectly elastic spheres, and that is completely time reversible. You're not losing any information. Why is entropy always increasing? Okay, that's one of the confusions, and that's the easy one, right? First of all, let's be very clear, right? Now let's be a little more careful. I want to call this the solution to the Boltzmann equation as not F1 anymore, okay? I want to call the solution of the Boltzmann equation as F1b, just to be precise, okay? So let's do that here. Let's call it, wherever F1 is, let's call it F1b. Okay, so and then I'm going to call this as HB. And this is what either increases or stays the same for all time. Okay, regardless of whatever boundary condition you start in, this is true. Okay, so that's what the H theorem gives you. But this sounds a little suspicious. Okay, so now let's go back to F1. Okay, now I want to define the true F1. Okay, so the true F1, I'll just call it F1, right, is obtained by solving the Liouville PDE. So first you solve the Liouville PDE. I'll just call it L, okay? This is the Liouville PDE that we saw. I'll just call this equation L, right? If you solve that equation, you get Pn. And then if you marginalize Pn, you basically get F1, okay? So I'll call it F1T, or let's call it F1L, okay? So let's call it F1L, okay? 2 dB2 all the way to dRn dVn, okay? So remember, the difference between F1L and F1B is because of all of the assumptions we made in deriving the Boltzmann equation or in closing the Boltzmann equation, okay? So Liouville is exact, okay? The first BBGKY equation is also exact, right? Liouville is as Liouville, we solve for Pn in Liouville, we solve for F1 in BBGKY, but it is unclosed. This is exact and closed, but this is exact and unclosed, right? So then you make some approximations, which is molecular chaos, Boltzmann grad limit, etc. And so we get the Boltzmann equation. And with the Boltzmann equation, we get F1B. Okay, so let's call this F1L, F1B, right? So these are not the same things. This is an approximation to F1L, okay? So let's now state some facts here, okay? The n particle, okay, let's go fact by fact, okay? Let's call this fact 1. Well, let's call this fact 1 because you can prove it. You can prove this rigorously, and it's an easy proof. So let's call this fact 1. Okay, so now let's fact 2. If you have the n particle PDF, basically the solution to the Liouville equation, integral Pn log Pn, right? Let's define this as H L n. Okay, it's a minus. This is over this entire 6n sigma space. I'm just going to call it Pn. Okay, so this is over d sigma n, right? Let's define the entropy corresponding to the Liouville equation, okay? So it is easy to see that this would always be 0, right? You have precisely reversible dynamics. You have time reversal symmetry. And just like we've seen in earlier examples, if you start with an initial condition that has some understanding of the microstates, you're not removing any amount of information from Pn. for all time, right? So you're not losing any information. So there is no mechanism for this, for the this basically called the Gibbs entropy. So there is no mechanism for the Gibbs entropy to change. You're neither adding nor removing information, no matter what initial condition you start in and what initial condition you end up in. Okay, so there is just no issue. Okay, so let's call this as HNL. Let's call this as S Gibbs. All right, let's go to fact 3. Well, what have we seen so far? So far, we've seen that dH1b by dt is always greater than or equal to 0. This is this one particle marginal from the Boltzmann equation. We've also seen that dH n, this is the Gibbs entropy, right? So this is by dt equal to 0, right? So fact 3 is, right, so again, if I define F1 Liouville as the marginalization of Pn, this is not entropy just yet. Sorry about that. dr2, dv2, all the way to drn, dvn. If this is the case, then, and we define h1l as integral minus f1l log f1l dv1, then dh1l by dt can be greater than or equal to 0 or can be lesser than or equal to 0. Okay. So this is not the same as the Boltzmann entropy. Okay. And the reason is, let's write the following. Okay. So let's write h of f1l, right? Let's say we have n of those, one for each of the particles, and if the particles are indistinguishable and they're initially, random, etc., etc., then you can write this as hn plus t. Okay, so this term, this is basically the Gibbs entropy. We've seen before, and this is all of the correlations. Okay, generally, not always, you can say tau would be greater than 0, right? Not always. And it is generally greater than 0 because, just look at these two things. Okay, think of that Venn diagram that we always see, and that we've seen before. N times f1. So remember, this is a constant, and correlation, think of this as mutual information. More or less, correlations always build up in time, but there may be a particular initial condition, or there may be, some circumstance where this can drop. Okay, when tau drops, this one also has to drop. Okay, but for most initial conditions, and for most scenarios, h1l will be increasing, but locally in time, h1l can be decreasing. Okay, remember h1, this may be a little counterintuitive to you because you would say, oh, if I marginalize, I'm actually throwing away information. And so my entropy should increase, right? You are generally correct in your intuition, but you're not accounting for the fact that there are some possible scenarios or initial conditions at which locally your entropy can, locally your correlations can lead to a reduction of entropy. Okay. So that is fact 3, that maybe a compact way of stating it is dH1L by dt is not always greater than 0. Okay, whereas the Boltzmann entropy is always greater than or equal to 0, because you have actually built irreversibility, or you've basically broken time symmetry here. So time symmetry broken by molecular chaos assumption. You're assuming that just before collision, things are uncorrelated, right? So going forward and in time and backward in time, they're not the same, okay? Whereas in the Liouville case, or in the exact case, there may be some conditions that may conspire to reduce the correlations locally, okay? But generally, your intuition is correct. Okay, so that is fact number 3. And generally, confusion comes because people do not distinguish F1B and F1L. Okay, F1L is exact in the sense that if you marginalize Pn, then you get F1L. Okay, so this is inexact, right? Because in deriving the Boltzmann equation, you made some approximations and you've broken time symmetry. All right, so that's an important fact. And again, the way to think about this is, okay, let's do, so far there were a bunch of details and, a bunch of math. Let's just write all of this in plain English, okay? So logical structure, 1, microscopic laws, time symmetric, which is why Gibbs entropy does not change. Going forward, backward, everything is the same. You can reverse any situation. But Boltzmann equation is time asymmetric. And it is time asymmetric because of the molecular chaos assumption. You said pre-collision pairs are uncorrelated. Now, here is something very interesting, right? The Boltzmann equation comes from the mid to late 19th century. And for 100 years, we just had to live with the fact that the Boltzmann equation was approximate. How approximate? It was hard to quantify, okay? But in 1975, a gentleman by the name of Lanford showed that if the initial condition is factorizable, and by factorizable, all he means is Pn of R1, V1, blah, 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 Rn, Vn, 0 at time t equal to 0 is written as the one particle marginal corresponding to R1, V1, the of the first particle, the one particle marginal of the second particle, R2V2, etc., etc. Okay, F1 of the nth particle. Effectively, what this condition says is, if the particles are initially uncorrelated, then for a short amount of time, F1b converges to F1L. Okay. And this was a major deal because it was the first time people had rigorously proved, or anyone had rigorously proved, that the Boltzmann equation converges to the marginal of the Liouville equation under some heavy mathematical conditions, but it was shown. Okay, so that's kind of nice that we had that. But so this was 1975. In 2025, a group of mathematicians, and two of those are actually at Michigan, and the faculty's name is Zahir Hani. I think Deng-Hani and Ma are the three mathematicians, and two of those are actually at the University of Michigan. They showed something remarkable. It's a 160-page paper, a little bit hard to read, but what it says is something very beautiful. It says, it starts with the same point that Lanford started. Okay, it says, if the initial condition is factorizable in this form, then F1b, F1L for all times converges. Okay, and when you say converges, it is in a specific sense, and there are a few technical details, but this is incredible. It is incredible because this is for just a very short amount of time, right? This actually, if I remember well, this was actually even less than the mean free time. Maybe it was less than a half of the mean free time, whereas this is for all times. Okay, so this is a very significant result. The papers are still under review for the past year. They published two papers. The first one was 160 pages. The second one was maybe slightly shorter, but still long. And but because they were able to prove it, basically Hilbert's sixth problem of Hilbert was basically this exact problem, right? Can you show that you can go from elastic hard sphere dynamics to the Boltzmann equation precisely in some sense, and then from Boltzmann equation to the equations of fluid dynamics? Okay, so that was done. So this is a very neat thing. Okay, so one technical point that I want, there are a couple of things that I want to talk about. The first one is, how strong is this assumption? Okay, why? I mean, this seems like something that is very restrictive, and I do agree. In the Lanford case, I would say it is very restrictive because, as I said, it is only true for a very short amount of time. So if the initial condition was that, and you can only go less than some mean free time, it's not that significant. But what Zahir Hani and his group have shown is significant because, let's say, when the universe began, particles were uncorrelated in this form, and that's probably not a terrible assumption. We'll get to that soon. But why this matters is, okay, we gave that initial condition, and then for all times later than that, you can imagine all kinds of collisions happen. entropy is more or less going to be increasing all the time, as given by the Boltzmann equation. And the Boltzmann equation is also a valid solution, more or less, for all times, given that initial condition. Okay, so that's why this is important. And this kind of, I mean, there is historically, and if you, again, one other point I want to make, if this is the initial condition, then almost always entropies, the one particle entropy is going to be increasing. Okay, not always, because there may be some strange local, I mean, if I want to make a plot, if that was the initial condition, and this is the one particle entropy, right? So initially, this is the entropy, and then I would say, for the most part, things would be increasing, but it is locally possible that you can have some fluctuations. Okay, this is how entropy would evolve if this was the initial condition. And then it gets a little philosophical. Why should, I mean, the answer to why is the entropy of the universe increasing even though it is a closed system? Okay, so that's called, I mean, the correct philosophical frame for that is the so-called past hypothesis. I think a whole bunch of people like Penrose and others have mentioned, have given a lot of their thoughts on it. But the idea is the initial condition of the entropy, the initial condition of the universe corresponded to a low entropy state. Okay, so, and hence, for the most part, entropy is always increasing in the universe. Okay, if the initial condition of the universe was not a low entropy state, then of course you don't expect the entropy to be increasing. All right, so I want to end with one final thing. Okay, and that one final thing is, how does all of this relate to the thermodynamic entropy? Okay, so far we've seen the Gibbs entropy, and we have seen the entropy corresponding to the one particle marginal, both for the true F1 as well as for the Boltzmann F1. The only thing is, what about thermodynamic entropy? Okay, so let's call it S thermo. And the way, so remember, our S Boltzmann was minus integral F1 B ln F1 B dx dv. Okay, this was, sorry, let me be consistent here. dr1 dv1, okay, in d1 sigma. Okay, this was S Boltzmann, and the one particle Liouville entropy was also very similar, right? The one particle Liouville entropy, you just replace the B here by L, and there you have it. Okay, so S thermo, you can, okay, let me write that. S, what did we give the name? H1L. Okay, let's be more precise. I'm known to be a little sloppy with nomenclature. Sometimes it's by design, sometimes it's just me. Okay, so this is H1B, and then there is H1L, which is minus integral F1. Did we call it L here? Yeah, F1L, F1L, dr1 EV1. And we know that, by Zahar-Hani's group, these two things converge. So in the same way, you can define S thermo. This is thermodynamic entropy that you study in your first year of undergrad, or whenever you take your class. So this is N, KB. These are all constants for this given problem. So nothing controversial there. F1, we've seen before, ln F1. And there is a little factor here, okay? And that little factor has something to do with the volume of the phase space, but I'll just write it. Okay, so this is thermodynamic entropy. Well, you can ignore these two. I mean, for a given system, right, you can ignore these two things. So it is very much related to the quantities that we've been seeing earlier. Okay. So in any case, that is really what I wanted to say here. And the most important things are the three facts that we saw earlier. Okay, where is fact 3? Right. So this is the punchline of the whole thing, right? The Gibbs entropy does not change. The Boltzmann entropy always increases. And the one particle Liouville entropy, for the most part, increases. You can have some very local fluctuations. And particularly if your initial condition was perfectly uncorrelated, then in the particular Boltzmann grad limit, again, I do want to mention this, okay? So both of these theorems are in the Boltzmann grad limit, both this one as well as this one. And for this particular initial condition, okay? But Lanford is only for very short time, and this is for all time, okay? So that's really what I wanted to say. And then I had this, the two English things that I wrote, yeah. So the microscopic laws are time symmetric, whereas the Boltzmann equation is time asymmetric because you broke time symmetry, okay? And that is why entropy is always guaranteed to increase, no matter what the initial condition is. All right, that is all I had to say. Thank you very much.